This video is going to bring up some topics related to things that you'll see in a practical lab setting, but that also come up in a lot of problems because in chemistry, we do most of our reactions in solution. So we're going to talk about concentration, which is how we measure how much of something is in solution, and then stoichiometry, which is just the word that chemists use when they're talking about mole relationships. So we're going to talk about those mole relationships within a solution. Eventually, in the next module, you'll see come up talking about those relationships within reactions. So in general chemistry, most of our reactions are in solutions that are made with water. So we do what we call aqueous solutions. So an aqueous solution just means that you've used water. And the way that we show that, and this will again come up when we talk about reactions, is we do parentheses with an AQ after the listing of whatever compound is dissolved. So one of the examples that we're going to look at in a little bit is a sodium nitrate solution. So sodium nitrate, the whole formula, if you see an AQ after that, it means that it's dissolved in water. So concentration, describing concentration can be qualitative, and these will be words that you have heard and used before. So qualitatively, we could say that something is dilute or concentrated, and those are obviously relative terms, but they describe either having a little or a lot of something dissolved in that solution, or they could be quantitative, and one way that we will describe solution in a quantitative way is with something called molarity. Now, there are many other ways that we will describe concentration, including things like molality, and you could use something like parts per million, parts per billion. Occasionally, the mass percentage that we've already talked about will be used. The focus and what most people use is molarity, so we're going to start there, but those others, I promise, we'll talk about them when we need to use them. So molarity, this unit gets a capital M, and molarity is calculated as moles of solute, which is the thing that we're dissolving, over liters of solution. So the solution part, right, it's everything together, and that's really important. It's not just the solvent or the water, it is after you've mixed the solute into it. So, for example, if we had sodium chloride, aqueous, our calculation would be moles of sodium chloride over liters of solution, right? And now the solution, remember, is the NaCl and the water together. So the way that we make solutions will help you see kind of how and why we're using that volume of solution when we calculate molarity. So when you're making a solution, we use this piece of glassware called a volumetric flask, and it looks something like this. I'm obviously questioning my decision to draw this for you and not pull up a picture, but that's all right. And it comes with a little cap. But I'm not going to put the cap on here because we're going to talk about what you put in this flask to make a solution. We need the cap off to do that. So this is a volumetric, and it will only have one marking on it, somewhere around the neck. This will be a calibrated volume. So if you have a 100 ml volumetric flask, the only volume that you can measure with that is that 100 mils. And we use these to make solutions, so we'll know we have exactly 100 mils of our solution. All right, so in order to make this, if you were to fill this completely up with water and then add the solute, your volume would end up being bigger than it is supposed to be, right? And then you can't accurately use your volumetric flask because it's only calibrated to that one specific line. So the order in which you do things is really important. The first thing that you would do is measure out however many moles of solute you need and put that in. The second step would be to add some water. Now, not fill it totally up, but add a little bit of water, and then you shake it and swirl it, get all of the water to dissolve the solute that you've put in there. Once you've totally dissolved it, you can add more water to the fill line, and then you will know that you have a specific volume of your solution. You'll know how many moles of solute you put in there, and you will be able to calculate the molarity of that solution. So I'm going to pause, write out an example problem, and then we'll look at that calculation. So we are going to calculate the molarity of a solution where 45.4 grams of sodium nitrate is dissolved to make a total of 2.50 liters of solution. So we're given mass, and I mean, this is what you would do in lab. You would weigh out some mass. But for our molarity calculation, we need moles. So our first step is to find out how many moles of sodium nitrate we put into the flask. So 45.4 grams. I am not going to show the calculation of the molar mass here, just for the sake of keeping a short video, but you should show the calculation of the molar mass for any case where it's not given. And if you want, now's a good time for you to pause and practice doing this calculation to see if you end up with the same answer. All right, 1 mole of sodium nitrate weighs 84.995 grams. So 0.534 moles of sodium nitrate. And then my molarity calculation, right? Molarity, which is the capital M, it's moles of the solute, which is the sodium nitrate, over liters of solution. So this gives me 0.214, and then I use a capital M for my units. So this is a 0.214 molar sodium nitrate solution. All right. So in many cases, the solutions that we need, it's not practical, especially with students, to give you some things to weigh out. And then also to save space, say I always want to use a sodium hydroxide solution. If I'm storing this, I want to store it with a high concentration because it won't take up as much space. So when we go to use those solutions, we need to dilute them. And there is a dilution equation. So solution dilution, I can calculate if I dilute my solution, what its new molarity would be, or if I'm looking for a specific molarity, I can calculate what volume I need to dilute it to. So the dilution equation is M1V1 equals M2V2. And what this is saying is that the molarity times the volume for solution 1 is equal to the molarity times the volume for solution 2. So this might seem a little bit odd. I don't know if this will seem odd to you or not, but when you look at it as an equation, I don't know, I guess you maybe assume that the person who made it up knows what they're doing, but just so that you can explicitly see what's underneath here, the reason that these are equal is if you do molarity, which is moles per liter, times the volume in liters, you get moles. So what this is saying is that the moles in solution 1 is equal to the moles in solution 2, which has to be true, right? And if you're not removing or adding solute, the only thing you're doing is diluting the solvent with the solvent to get a different solution. The amount of solute is the same, so the number of moles would have to be the same. All right, let's do a practice with this one. So I won't pause this time. So this problem says you have 200 mils of a 15 molar sodium hydroxide solution. So this is pretty concentrated. What will the final volume be if you need to dilute it to a 2.5 molar solution? So it doesn't matter which one I make solution 1 and which I make solution 2, but let's just say solution 1 is the one that I'm starting with, and it has a molarity of 15 molar, and I have 200 mils, but I mean, technically if the volumes are the same, the units don't quite matter, but let's keep everything so that it would properly cancel. Moles per liter. If I multiply by liters, I'll get moles. So my 200 mils as liters is 0.200 liters. And I want to dilute this to a 2.5 molar solution. And volume 2 is what I'm looking for. So I'm looking for what this volume is. So M1V1 is 15 times 0.2 equals M2V2. And if I solve for V2, I get 1.20 liters. So I take all of my original 15 molar solution, I add water to it until the final volume is 1.2 liters, and my new solution will have a molarity of 2.50 liters. 2.50 molar, molarity, molar. All right, that's how you use the dilution equation. And stoichiometry in solution is the last point in this video. And it is related to some of the other stoichiometry we have already done, So for example, when we were doing combustion analysis, we used the fact that one molecule of carbon dioxide had one carbon atom in it. So 1 mole of CO2 had 1 mole of carbon. So we're going to use that, and then we're going to use one other thing that is related to what you learned when you were naming compounds. So what we're going to look at are 2 different things dissolving in water. I'm going to use some reaction notation that we haven't talked about yet, but it's probably come up in any textbook or resource. I promise that's coming. It's the very first thing in the next module. So let's look at 2 things dissolving. If I take sugar, which is C12H22O11, I take this solid sugar and I put it in some liquid water. What it turns into is C12H22O11 aqueous. Well, we've talked about the aqueous part. It just means that it is dissolved in water. And you have seen this, right? If you take sugar, you pour it in water, it disappears because it dissolves. And what you have are sugar molecules dissolved in water. If you take something like sodium chloride, take that solid, add it to water. And you have seen this as well, right? If you take salt, put it in water, it'll disappear because it dissolves. When salt dissolves in water, it turns into Na plus aqueous and Cl minus aqueous. So this is definitely different from what we saw with sugar. So the question is, why are they different? And how do we know that this is the case? So let's do a side-by-side comparison. The C12H22O11 versus NaCl. So the sugar, this is a molecular compound. It has covalent bonds. The sodium chloride is an ionic compound, so it has ionic bonds. The sugar, because it's a molecular compound with these covalent bonds, it doesn't split up when it goes into solution. We call this a non-electrolyte. The sodium chloride is an electrolyte. So what this means is that anything that is a molecular compound, a non-electrolyte, the molecule will be intact after dissolving. For an ionic compound, it splits into its component ions. Now, I want to do a special note here about polyatomic ions. These stay intact, but the ionic bonds break. So, for example, sodium nitrate is something that will dissolve in water. If we took NaNO3, put it in some water, you would get the ionic bond breaking, so the sodium would split up from the nitrate, but the nitrate as a polyatomic ion would completely stay together because those are covalent bonds. All right, so an example of how you might use this. So the question that we're going to answer with the information that we now know is, what is the concentration of OH minus ions in the 2.50 molar solution from earlier? And with this, I want to introduce a little bit more notation. So if we put something in brackets, that means concentration of. Now we'll still put units on it, so when we get our answer, it'll have units of molarity, but when we put brackets around something, that's another way of saying concentration. So what we know is that sodium hydroxide is an ionic compound. It's the sodium ion and the OH minus polyatomic ion. So when this splits up in solution, my ionic bond breaks, my covalent bond does not. So if I have one sodium hydroxide, I'm going to get one sodium and one hydroxide. So my 2.50 molar sodium hydroxide solution, in this solution, I get 1 mole of OH minus for every 1 mole of sodium hydroxide. So my concentration of OH minus is also 2.50 molar.